Once upon a time, there was a little metal ball, and it decided to demonstrate the law of conservation of momentum. Chapter 8, Momentum. Momentum is conserved for all collisions as long as external forces don't interfere. So we're talking about collisions inside the system. We've talked about inertia, and we said inertia was applied to things that weren't moving or were moving. We're going to talk in this chapter about ones that are moving. That's what we're talking about with momentum. So momentum, a moving object can have a large momentum if it has a large mass, a high speed, or both. You know, I think we all know that it's a lot harder to stop a large truck than a small car if they're both going at the same speed. If we think about a semi and a small car, you know, we know that both of them, if they're going the same speed, one of them is going to be a lot harder to stop. And the reason for that is the truck has more momentum. Okay, so when we're talking about that, we're talking about, as they say, inertia in motion. So we're talking about an object that's moving, it wants to continue at rest, you know, until something else is going to do something to it. So momentum is the mass of an object multiplied by its velocity, or we just sometimes say it is m times v, mass times velocity. And if we didn't care about the direction, we could say it's mass times speed, but this is the one that we will use all the time in here. It's what we always talk about, mass times velocity. So, new thing to remember, momentum, mass times velocity. If the car and the truck are moving at the same speed, the truck's going to have more momentum because it has more mass. Remember we said that momentum, mass times velocity. So if it's got more mass, it would have more momentum. However, if we have a fast car, if the car has a really big velocity compared to its mass, and the truck, you know, it's got a bigger mass but a really little velocity, then the car could have more momentum based on the fact that, you know, a fast car could have more momentum than a slow truck. And if it's not moving at all, when things are at rest, you know, velocity is 0, therefore m times v has got to be 0, so momentum is 0 for anything that is at rest, has no momentum. So here we have our truck rolling downhill. We've got a pair of roller skates. Actually, not a pair, it looks like just one. Rolling beside it. They're having a race. Which one has more momentum? Well, obviously the truck is going to have more momentum. Unless maybe you put the elephant on the roller skate. Can you think of a case where a roller skate and a truck would have the same momentum? So think about that. Can you think of a case where that would happen? They'd have the same momentum. So they give an answer of, well, yeah, sure. If the truck was going really, really slow, like maybe it's backing out of a driveway and it's only going to move at 1/100th of a meter per second. You know, you've got this big truck, and then you've got this 1 kilogram skate, but it's going 10 meters per second downhill really fast or something. They both have a momentum of 10. And, you know, I can think of another one that's even easier than that. If they're both stopped, they would both have 0 momentum. That would be even easier. All right, so let's talk about how momentum changes. And momentum changes depending on the force and how long that force acts on it. So if we're going to change the momentum, what's going to happen in order to change the momentum is you either have to change the velocity, or you have to change the mass, or you change both. Now, typically, we don't change a lot of masses. You know, I mean, an object pretty much stays what it is. So we're usually talking about changing the velocity of it. And the greater the force that we have that acts on it, well, the greater the velocity, right? That makes sense, doesn't it? F equals ma. So the more acceleration we have, that's going to affect the velocity, because acceleration is the rate of increase in velocity. So if we apply this force, or greater force, we're going to have a greater change in the velocity then. And if we're talking about impulse, impulse is force over a certain amount of time, both force and time. So the longer I can apply a force, the more it is going to have an effect on that object. So for instance, here's this guy pushing this car. If he applies a force for 5 seconds, he's going to change the momentum of the car a certain amount. If he applies that same force for 10 seconds, he's going to change the momentum of the car even more. Now, I have a question. In this day and age, why does he have to be pushing? You know, I think maybe they should both push. Of course, then the car would probably go up in the ditch, but it would be twice as much force, so it would go better. If we're talking about impulse, we said impulse is our force times the amount of time that we can apply that force. So force times time is known as impulse. And understand that the impulse is directly related to the change in momentum. So we've got a nice little formula. Force times time equals mass times velocity. And of course, we're talking about the change in one of those things is changing as we're looking at this. So if you want to have the biggest increase, the biggest change in momentum, what you want to do is apply your force for as long as possible. That's why, you know, they always talk about when you're hitting a baseball or you're swinging a golf club is that you want to have follow-through. Why do you want to have follow-through? For one simple reason. You want to increase time that you're applying that force. So the longer, the better the follow-through, you have, the more time you're going to be applying force to the object that you're hitting. So take a look at this golf ball and notice how, you know, look at this right here. Look at how misshapen the golf ball is. So when the club hits it for a fraction of a second here, this golf ball gets misshaped. And so we want this club to apply as much force to this for as long as possible. The longer we can put it in there, the more force or the more impulse. Not the more force. I mean, the force is there, but we can affect the velocity of it more by putting in more time in that with that force. So the golf club that strikes a golf ball is going to exert zero force on it before it comes in contact. So it can be moving really fast but not putting on any force. As soon as it hits the ball, it starts to distort the ball, and then it increases the speed of that ball. The force diminishes as the ball comes up to speed and returns to its shape. As the ball leaves the club now, the force is now gone, and you have applied all that force in just, you know, a fraction of a second from the time the club hits the ball on the tee to that time that the ball starts to move past or get away from the club. And so what we're going to talk about, and all those things change, so most time we're going to talk about average force. You know, it technically is going to be a little bit different when you first hit it and a little bit different when you're in the middle and a little bit different at the end. But we're going to just talk about average. That'll just be easier. We always like to make things easy in physics. All right, so let's talk about the opposite. Let's say you want to decrease momentum. You know, think about this. You're driving along in a car and you lose control, and you got a choice. You can either drive your car into a haystack or into a concrete wall. Now, well, I think most of us would probably pick the haystack. And so let's talk about why that would be a better choice. Why is it better to run through the haystack? Well, what are we going to do? If we go through the haystack, here's our car. certain mass, going pretty fast. He lost control, hits the haystack, okay? And now look at, we've got all this time. We're going to get through this thing, all this time. And if we have a lot of time, we don't have to have a lot of force to reduce this velocity to take it down. Now, hopefully, when he went through here, hopefully he didn't have his window open because that would be kind of messy. But it would be better than the alternative. The alternative would be running into the wall. And in this case, you know, it doesn't take long for this to happen. You hit the wall and crunch. But there's a huge force there, and then this is what happens to the car. All right, so the driver is either going to run into the haystack or he's going to run into the wall. In both cases, the momentum is decreased by the same impulse. But the difference is, one, force is big and time is small. And the other one, force is small and time is large. And if you're in the car, you don't like this one. So you go for this option, and we automatically would probably, I think, most of us, pick the haystack. You know, it's the same reason why you have dashboards in a car that are not rigid, that are, you know, they're left to, or they're softer so that they can do that, or airbags to slow down, you know, the person, rather than hitting the steering wheel in just a short amount with a lot of force, short amount of time with a lot of force. You know, airbags kind of increase the amount of time that you're slowing down. Or if you catch a ball with your hand, you know, you try to give a little bit when you do that. You know, or think about this. When you jump to the ground, I mean, if you jump from a long ways up, you should always bend your knees. You know, think about that. If you don't, you know, if you land stiff-legged on there, you're going to hurt yourself. Okay, so that's why when you jump, you kind of bend your knees a little bit to give a little ground. And the main reason is because you are trying to increase time. Therefore, you are decreasing the force by doing that. Or here's this boxer, and you know, a good boxer, when he gets hit, he's actually going to move away with the punch. So he's going to actually spend more time in contact with the glove, but because of it, the force is going to be less. On the other hand, the poor boxer, he is going to move in. So maybe there's very short time and a very large force, probably maybe, you know, 4,500 pounds of force, you know, hitting his jaw. That would be, you know, that was going to knock this guy out in most cases. So boxers always want to give with it. Okay? Or if you think about why a glass dish doesn't break when it hits a carpet versus if you drop it on cement, it's going to break. Well, most of you say, well, the carpet's got more give. Well, what does that mean? What does give mean? Give, very simple, means more time. Okay? More time slowing down. So if we have more time, that means less force on it when it hits. Or a safety net by acrobats, same thing. You know, all of them increase the time and therefore decrease the force. All right, here, answer this question. When a dish falls, will the impulse be less if it lands on a carpet than if it lands on a hard floor? Now think, it's not, you know, read the question, make sure you're answering this question. No, impulse is the same. What is changed or what is different is force or time. But the impulse, no, impulse is the same. Still takes the same amount of impulse to stop it. Okay? If a boxer is able to make the contact time 5 times longer by riding with the punch, how much will the force of the punch impact be reduced? So he's moving with the punch, takes 5 seconds. Or 5 times longer, not 5 seconds. How much will the force be reduced? Well, it would be reduced by 5 times.